A vinyl record and a phone stream can play the very same song. Same singer, same speakers, same ears, but they store that song in completely different ways, and that one difference is why every modern computer is digital. Welcome to Chapter 1, Why Bits Matter. By the end of this chapter, you will know what a bit is, how to count and measure with just two symbols, and how to add, subtract, and multiply in binary by hand. Think about a vinyl record and a music stream. Same singer, same speakers, same ears. Both carry the same song to you. But they store that song in two completely different ways. One is analog and one is digital. That difference is what this whole chapter is about. Let's look at the plan for this video. It has 4 parts. First, analog versus digital. What continuous and discrete really mean, and the 3 reasons the computing world chose digital. Second, bits and binary. The smallest unit of data, place values, and how to count with only 2 symbols. Third, bytes and units. How bits group into bytes, and why a 500 gigabyte drive can look like it lost some space. And fourth, the centerpiece. Binary arithmetic done by hand, with carries and borrows moving column by column. Let's start with the most basic question. What is the difference between an analog signal and a digital signal? Picture measuring the temperature outside. The left side of this figure shows an analog signal. It is a smooth wave that passes through every possible value as it rises and falls, with no gaps at all. The right side shows a digital signal. Instead of a smooth wave, it moves in steps. We will look closely at both sides next. Let's focus on the analog panel on the left. An analog signal is a continuously varying quantity. It can take any value within its range. Between any 2 values, there are infinitely many more. A mercury thermometer, a clock with sweeping hands, a ramp going up, all analog. The key word is continuous. Now let's focus on the digital panel. A digital signal is not allowed to take any value. It is restricted to a finite set of discrete levels. The simplest one has just 2 levels, which we call 0 and 1. See the dashed threshold line running across the panel. Anything above the line counts as 1. Anything below it counts as 0. The smooth wave has been forced onto a staircase. Let's walk up the digital staircase one step at a time. At the first step, the signal holds 1 fixed level. At the second step, it has jumped up to the next allowed level. Third step, it holds that new level steadily. Fourth step, another clean jump. Fifth step, notice there is nothing between the steps. Sixth step, the signal is never halfway up. Seventh step, still snapping to an exact level. And the 8th step here on the right. That is the whole idea of digital. A ramp is analog because you can stand anywhere on it. A staircase is digital because you must stand on 1 step. Everything else in this chapter is built on this. So why did the computing world choose digital? The first reason is copying. Look at the top row of this figure, the analog copies. The first copy is the original plus a little random noise. The second copy adds more noise on top of that. By the third copy, the wave has drifted noticeably from where it started. After 100 copies, an analog signal can be unrecognizable. This is why a cassette tape sounds worse every time you copy it. Now look at the bottom row, the digital copies. A digital receiver does something an analog one cannot. At each step it asks one yes or no question. Is this value above the threshold or below it? As long as the noise stays small enough, it does not push a value across the line, so the first copy is rebuilt as a perfectly clean 0 or 1. The second copy is clean too, no noise carries forward. And the third copy is identical to the original. You can copy a digital file 1,000,000 times, and the millionth copy still matches the first. Let's gather the 3 reasons digital won, one at a time. First, noise immunity. As long as disturbances stay small enough, they do not cross the threshold, so the stored data stays safe. Second, perfect copying. Because the signal is rebuilt at every step, the millionth copy is identical to the original. There is no generation loss. Third, logic operations. 2 levels map naturally onto false and true, so you can build circuits that do and, or, and not. Connect enough of them and you get a computer. Each of these 3 would be reason enough on its own. If everything is zeros and ones, how do we count? To answer that, we need the bit and the binary number system. The simplest digital signal has 2 levels, on or off, high or low, true or false. A single one of those 2 valued choices is called a bit. The word bit is short for binary digit. It is the smallest unit of data, and it has exactly 2 possible values, 0 or 1. 1 bit on its own can only tell 2 things apart, but combine enough bits and you can represent anything at all: numbers, letters, colors, sound, even instructions. The rest of this book is about how. Just like decimal, binary uses place value, but instead of each position being worth 10 times the one to its right, each position is worth 2 times as much. The rightmost bit is worth 1. The next bit to the left is worth 2. The next one is worth 4. And the next is worth 8. Each weight is double the one before it, and every weight is a power of 2. Memorizing the powers of 2 will save you time again and again. Let's convert the binary number 1011 to decimal, column by column. The method is the same one you already use in decimal without thinking. Multiply each digit by its place value, then add. The leftmost bit is 1, times the place value 8 gives 8. The next bit is 0, times 4 gives 0. A 0 bit adds nothing. The next bit is 1, times 2 gives 2. The last bit is 1, times 1 gives 1. Now add the contributions down the page. 8 plus 0 plus 2 plus 1 equals 11. So binary 1011 is decimal 11. Let's count from 0 up to 7 in binary and watch the columns. The 1's column on the right flips every single step. 0, 1, 0, 1. The 2's column flips every 2 steps. The 4's column flips every 4 steps. Each column toggles at half the rate of the column to its right. Think of it like the wheels of an odometer in a car, where the 10's wheel turns once for every 10 turns of the 1's wheel. In binary, each column turns once for every 2 turns of the column to its right. The 1's column flips every step, the 2's every 2, the 4's every 4. Once you see this rhythm, counting in binary becomes automatic. Bits rarely travel alone. Let's group them into bytes, and then learn how storage is actually measured. A single bit is not very useful on its own, so we group bits together and the groups have names. The smallest group is the nibble, 4 bits. Next is the byte, 8 bits. This is the one that matters most, and a byte is 2 nibbles. The largest is the word. 32 or 64 bits on modern machines. A 32-bit word is 4 bytes, and a 64-bit word is 8 bytes. Let's pin down the three names. A nibble is 4 bits. It can represent 2 to the 4th, which is 16 values, 0 through 15. The name is a little joke. A nibble is a small byte of a byte. A byte is 8 bits. It can represent 2 to the 8th, which is 256 values, 0 through 255. The byte is the standard addressable unit of memory, the smallest chunk most systems read or write at once. A word is the natural size a processor works within one operation, typically 32 or 64 bits today. Bytes are small, so we need prefixes for big quantities. This first system is the decimal SI prefixes, based on powers of 1000. Kilo is 1000 bytes. Mega is 1 million bytes. Giga is 1 billion bytes. Tera is 1 trillion bytes. Each step multiplies by 1,000. Hard drive makers, network speeds, and official standards all use these SI prefixes. When a drive says 500 gigabytes, it means exactly 500 billion bytes. This second system is the binary IEC prefixes. Computer memory is organized in powers of 2, and 2 to the 10th, which is 1024, is very close to 1000. So a second ladder exists where each rung is 1024 times the last. A kilobyte is 1024 bytes. A megabyte is about 1 million bytes. A gigabyte is about 1 billion bytes. A terabyte is about 1 trillion bytes. The letters B, I in kibai and mebai and jibai stand for binary. These names look strange at first, but they exist to remove a real confusion. Now watch the two ladders spread apart. At the kilo level, they differ by only about 2.4%. But the gap grows as the numbers get bigger. At the tera level, it reaches about 10%. This is the famous case of the missing hard drive space. A drive advertised as 500 gigabytes really is 500 billion bytes. But software that measures in binary gigabytes divides by 1024 3 times and gets about 465.7. The number shown falls by about 34, but it is the same bytes, only the unit changed from gigabytes to gigabytes. Nothing is lost. The space is not actually missing. The drive counts in SI gigabytes and the software reports in binary gigabytes. It is a unit mismatch, not lost storage. Now the centerpiece. You can write numbers in binary and measure their storage, but can you compute with them? Yes, you can, and it works exactly like the arithmetic you learned in grade school. The only difference is that each column overflows after 1 instead of after 9. In decimal, you memorized an addition table with 100 entries. Binary has only 4. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And the only new one, 1 plus 1 is 1 0 in binary, that is 1 0, not 10. You write a 0 as the sum digit and you carry a 1 to the next column. Watch that amber carry. In the worked examples, it will travel one column to the left, beat by beat. Let's add 1011, which is 11, and 0110, which is 6. We work from the right, one column at a time, and I will keep the spotlight on the column we are doing right now. The rightmost column, 1 plus 0 is 1. Write 1 and there is no carry. The next column, 1 plus 1 is 1 0. Write 0 and carry a 1, watch it appear in amber above the next column to the left. The next column, 0 plus 1 plus the amber carry that just arrived, is 1 0 again. Write 0 and the amber carry steps one more column to the left. The next column, 1 plus 0 plus the carry is 1 0. Write 0 and the carry steps left once more. That last carry has nowhere to sit, so it becomes a new leading digit, 1. Read the answer from left to right, 10001. That is 17 in decimal. Notice the amber carry never jumped. It stepped one column to the left each time. Let's confirm it with the computer. This is the output of a short Python check. 1011 plus 0110 gives 10001, which is 17, and the plain decimal check agrees. 11 plus 6 is 17. Our hand calculation was exactly right. Subtraction works column by column too, but instead of carrying, you borrow. When the top digit is smaller than the bottom digit, you borrow 1 from the next column to the left. That borrowed 1 is worth 2 in your current column, just as a borrow in decimal is worth 10. The easy cases are simple. 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0. The tricky one is 0 minus 1, which forces a borrow. And just like the carry, the borrow will travel in amber, one column to the left at a time. Let's start with a clean case that needs no borrowing. 1101, which is 13, minus 0101, which is 5. The rightmost column, 1 minus 1 is 0. The next column, 0 minus 0 is 0. The next column, 1 minus 1 is 0. The leftmost column, 1 minus 0 is 1. The bar row above stays empty the whole time. Read the answer, 1000, which is 8, and 13 minus 5 really is 8. Now let's see one where the borrow has to travel. Now a subtraction where the borrow has to travel. 1000, which is 8, minus 0001, which is 1. Start at the rightmost column, 0 minus 1. We cannot do that, so we must borrow from the column on the left. But that column is a 0. It has nothing to lend. So the borrow request moves further left in amber. The next column is also a 0, still nothing to lend. So the request steps left again. Now we reach the leftmost column, which holds a 1. It lends, and that one becomes a 0. Now the borrow settles back toward the right. Each 0 it passed through becomes a 1, and the rightmost column finally has its 2. 2 minus 1 is 1. Read the answer, 0111, which is 7, and 8 minus 1 is 7. See how the single amber borrow stepped left through the zeros until it found a 1 to lend. Let's check both subtractions with the computer. 1101 minus 0101 is 1000. That is 13 minus 5 equals 8. And 1000 minus 0001 is 0111. That is 8 minus 1 equals 7. Both agree with our handwork. Notice how the borrow chain rippled across 3 columns, just like borrowing from a number like 1000 in decimal. One short multiplication to finish. Binary multiplication uses shift and add, the same long multiplication method you know from decimal, but easier because each multiplier bit is either 0 or 1. Let's multiply 1011, which is 11, by 101, which is 5. Bit 0 of the multiplier is 1, so we copy the multiplicand, 1011. Bit 1 is 0, so this partial product is all zeros. Bit 2 is 1, So we copy the multiplicand shifted left by 2 places, 101100. Now add the partial products. The result is 110111, which is 55, and 11 times 5 is 55. The trick is that multiplying by a power of 2 is just shifting left, adding zeros on the right. Let's gather what this chapter gave you. 4 takeaways to carry with you. First, digital beats analog for computing. Because of noise immunity, perfect copying, and the ability to do logic. Second, a bit is a binary digit, a 0 or a 1. Each place value is a power of 2, doubling as you move left. You convert to decimal by multiplying each digit by its place value and adding. Third, bits group into bytes, and the 2 prefix systems, SI in powers of 1000 and IEC in powers of 1024, explain the missing storage on a new drive. Fourth, binary arithmetic is just the grade school arithmetic you already know. The carries and borrows simply move column by column, and each column overflows after 1 instead of after 9. That is Chapter 1. You can now count in binary, measure storage, and add, subtract, and multiply by hand. But long strings of zeros and ones get unwieldy quickly. In Chapter 2, we introduce hexadecimal, which lets you write a long binary string compactly, 4 bits at a time. See you there.